Next, I'd like to welcome Meenakshi Sharma, Technical Product Manager with the Machine Learning Platforms Group at Wayfair, a leading global home retail company. Her team is primarily responsible for delivering state-of-the-art ML platforms and solutions to be leveraged by data scientists and machine learning engineers. With that, over to you, Meenakshi.
Hello, everyone. Thanks for joining for this session. I'm Meenakshi Sharma. I'm a product manager at Wayfair. I work with machine learning platforms team, and today I'm going to talk about building capabilities for ML model development and training. And I'm going to share my perspective and while we are on this journey of building these platforms, what are the challenges and best practices and lessons learned? So let's dive in. Here's quick outline, introduction to the company, to the team, some of the use cases that we solve for in the e-commerce domain, and then typical ML lifecycle, just to set the stage. And then we quickly go over the challenges, design considerations while you're building such platforms, along with the best practices. All right. So who are we? Wayfair is a e-commerce platform. It provides an environment where our suppliers and customers are able to, sell their products and sell and purchase the products as easily as possible. Our technology and services empowers these platforms, and we focus on providing the best experiences for our stakeholders. And we are a growing community of millions of active users and the several thousands of suppliers. My team specifically caters to the technology division, which is several thousands of engineers and data scientists. Data scientists are aligned with business verticals such as marketing and operations as they solve for these niche use cases, while our team is centralized, which serves them across the board, building the ML tools that they can use in any of these ML lifecycle. All right. So, what are some of these use cases? Um, Within the e-commerce platform, um, we have our users starting from pre-order to post-order. We solve for several use cases. Um, we collect a lot of data right from what the customer is purchasing, the inventory, and so this rich amount of data allows us to solve for some of these interesting problems, which could be related to marketing, search, and customer service. For example, we know from the historical data what specific customer has been purchasing and browsing for. Based on that, we can target our marketing efforts and help enhance the add to cart rates based on that. Similarly, when you come to our website, based on your browsing history, we can personalize those experiences as well as provide you relevant discounts based on your location and other input factors. Last but not the least, we have thousands of agents helping you with your products and helping you with your orders. And during these inbound calls, we can help optimize these routing of the calls to different departments and optimize the process, as well as give best experience to our users. Another example is use this data to also have to help design best training for our customer agents. And there are several of these use cases that our data scientist teams are currently working on. All right, so let's take a look at the typical machine learning lifecycle. It's a simplified view where data scientists begin by exploring the data. They then begin to pre-process the data, removing bad data, duplicates, and additional getting additional statistics and summaries, ensuring that this is the data they want to build their model on. Then they move to experimentation and training, working with fine tuning their models, to deployment where they deploy their model, productionize that, leading to continuous monitoring, looking for any opportunities for training. So what's important is who are the actors involved during this process. A model developer, on one hand, owns the development of the model. In many cases, they'll be working hand in hand with ML engineers who would help them productionize and operationalize these models. This would include building the pipelines, and also the making sure the relevant artifacts are created and deployed to the production environments. At the same time, we also have model consumers. Your model might be consumed by some downstream team, and or it might be consumed by business users for insights. So these are also very relevant things to keep in mind while you're designing these systems. And last but not the least, the platforms providers like us, we span across the board, and we empower empower our data scientists uh, to work with the tools that are most optimized for their specific needs at each of stages. All right. So these, developing ML ops pipelines presents challenges in many ways. What I have done in this slide is try to look at it from the lens of people, process, and technology. We already saw there are so many actors involved. Um, so if you think of managing the people, there's a lot of training, and making sure these specialized skill sets are well groomed, they have careers, um, and providing them a good coaching and career planning is very critical and also very challenging. Um, in terms of processes, there's a lot of standardization, ensuring the quality of data that is provided from the data engineering pipelines are well formed. Um, since there are so many teams involved, how do we engage them well? So these are all the challenges in the people and process areas. In next slides, I'll be focusing more around technology challenges and speaking to the fact that there's a range of data, both in terms of variety and the sizes that different teams are processing and leveraging for developing their models. Um, these data processing needs present its own challenges. The amount of power, compute power needed differs for different teams. Also, there'll be avenues where different steps could be automated, and all of this is something that can be leveraged using relevant technology. All right, so let's move to let's talk about some of these challenges, and let's continue the discussion with the compute. Um, so we support a range of data science teams, and like I said before, they will have different set of data sets. It could be text, it could be structured, unstructured, or images. And hence, some of these models, while processing, their compute needs will vary. Some of them will be CPU versus memory bound, and some of them may also need specialized hardware like GPUs for accelerated execution. So this can be a challenge. Getting access to these resources can be a challenge, as well as optimally managing the utilization of resources can also present its challenge. Let's move to dependency management. So when these models, usually they are developed in Python or R, they require a different set of libraries. These libraries, when you are deploying, if you are using some shared compute, then often present some conflicts. Also, in some cases, you're not able to use the versions that you want, maybe move to the next latest versions, because you're sharing, let's say, a bare metal machine for high amount of GPUs. And this can present challenge for our data science teams because they're not able to move as fast as they want. All right. Repeatability. Data science, data science models, um, just like software models, when something goes wrong, you want to rerun and watch and compare the results, as well as if there are, let's say you have a new model, you want to compare it with the model that was developed maybe few weeks ago. uh, you want to be able to do that, but it's a little bit more challenging than compared to, say, a software. Here you also need the data set and the parameters that were used to develop that model. So that process has to be repeatable for a data scientist to be able to run and rerun it with reliability. Um, Next, moving to collaboration. So like we already saw, there are so many actors involved in the data science pipe development. Um, Data science teams often share and collaborate within their team members or outside their own team. For example, consider they have to get some they have to get some informal review of code walkthrough with their um, team member, and they have a Jupyter notebook. So they would like to share that notebook within their team. Additionally, let's say they are debugging some issue, they like to share the logs available to a platforms team. So in that case, wherever these pipelines are running, they should be able to share these relevant artifacts without compromising the security needs. All right. Coming to velocity, data science development is in um, different steps, and each of these steps can be slowed down because of many reasons. For example, in code development, there's a lot of data wrangling. When there is a handoff from data scientist to an ML engineer, there could be a lot of waiting, or maybe the results were not compliant to what were not the same when data scientists handed it off to the ML engineers. So ensuring that the development and training happens in a faster way is also one of the key challenges and key goals while developing these systems. Let's go to portability. Um, if your data scientists are using different systems, let's say Macintosh versus Windows and different environments, um, it's not easy for them to just share their code across different systems without issues and system dependencies. So portability becomes also a good factor to consider, and it also helps with velocity and repeatability. Last one that I'm going to discuss today is testing. Data science models, just like software, need to be tested at unit level, at integration levels, and um, often you'll see some of the teams might not be engaged, or it's a very long process, so testing may often be ignored. But this is also something where you need to provide frameworks and tools for fast and repeatable testing. And there's so much more, but I'll just continue with the next uh, examples. What I'm going to do is take an example of a problem statement, and we'll see what kind of design considerations we might have for solving this problem. And then we'll take this general problem and look at one of the potential solution that would fit the bill and address those requirements. And so this will help us give an opportunity to think about how we are designing such systems, what are the design considerations, and let's start with our first example. So let's say we need to develop an environment where users can develop models in a scalable fashion. We already discussed compute has been an issue, and that's where the scalability factor comes in. Um, so what are potential requirements? Uh, Data scientists would need an interface. They'll need continuous integration with development pipelines, for example, GitHub and version management. While they're developing their code, they need to store the immediate results, and the compute attached should be scalable. So that's some set of requirements. Um, so what could be sample solution attributes? One of the ways you could solve this is offer hosted Jupyter notebooks. Jupyter is a familiar framework for familiar development interface for data scientists, and it's also open source. So you can host these notebooks on virtual machines. You can provide a self-service way for data scientists to get access to these resources. Apart from that, you'll have to add connectivity to the existing deployment pipelines and version control that your company is using. um, and then you can add persistent storage to these systems as a means to when you're working on your laptop, you have file mounts, and so persistent storage in that sense can be added to these um, machines. And then to provide scalability in some sense, you can add the flexibility to choose machine types and different configurations that would offer them range of resources from RAM and CPU and GPU. So that way they can scale as their need changes. All right, so let's look at the second issue or problem statement. Let's say within this development environment, they need to perform a lot of computations on large data set, and it could be millions of rows, and they are in the exploration phase, but they'd like to get some summary statistics and look at the data in a very fast manner. So the requirements is high speed computations on large data set, lower latency, and again, you need an interface to author the code. So what could be a sample solution? In this case, you could leverage existing distributed frameworks. Um, uh, PySpark is one of the open source familiar distributed frameworks, and you could allow users to work on machines that connect with these distributed um, uh, clusters running distributed computing like Hadoop clusters. What users can then do have these client machines that would interact that would submit interactive jobs to these clusters and get their results as in few seconds. So now the users have a mechanism to run fast computations on big data sets with a Jupyter notebook hosted on their client machines. So this is one of the solutions that, again, solves the need for a very specific use case. All right, moving to our last example. Let's say you now need to develop uh, an environment for training ML models. Training again is a very repetitive process, and a lot of parameter tuning happens. Often the resources that you need may vary. One team might just need a few CPUs compared to other teams. They might need GPUs. So existing platforms uh, uh, more often people might have the on-premise servers that are basically shared by multiple teams, and what it leads to is noisy neighbors and limited compute because you are bound to the machine and their resources. So what would you like to do is offer a stable, isolated environment that where you could run fast jobs in preferentially distributed manner. Um, at the same time, this should be easy to debug and monitor, because as jobs are running, you would like to see if it's what's the status, if it failed, why it failed. You'd like to investigate. Um, Also, because this is data, this training, you need to also integrate with data features. And so if you have feature library, feature stores, or model serving, model registry, then you'd like to connect with these systems. Also, you like to scale horizontally and vertically depending on the size and nature of the training data set. Cool. So what are sample solution attributes in this case? Um, because distributed computing can be performed in different ways. You'd like to support popular frameworks out of the box, like Horoward, Dask, PySpark. Um, and to allow users to easily perform debugging, you'll also like to provide logs as these jobs are running. Um, Dependency management is also one of the issues, or in one of the requirements. So you would want to provide the opportunity for users to upload their um, uh, requirements for this training. At the same time, um, to integrate better with the other tools and services, you could develop custom libraries and APIs to integrate with them. In this case, what would be uh, what's applicable is the ephemeral compute, because the needs may differ, and users may want to scale horizontally and vertically as specified before. So you could also allow to run these jobs in an ephemeral manner. And so users are able to select different machine types, and at the same time, while it's running, they can span out multiple jobs. All right. So let's quickly look at some of the design considerations. I hope in the last few examples, some of them were already covered. So let me touch base on few that I didn't in the last few slides. For example, build versus buy. In machine learning industry, as of now, there are a lot of open source solutions. There's a lot of cloud based solutions. So what you would want to do before solutioning is evaluate the trade-offs for your team, for your company, in that whichever stage of maturity you are, like, and the goal of your project, whether you want to build this product or you want to buy this from existing a vendor. Um, other Also define the metrics and KPIs for your products. Like, you would want to capture the product usage data, user growth data. So number of um, basically number of jobs submitted, number of job failures. This is also something you'll want to integrate if you're building this, or also look for these features when you're buying from vendors. Um, in our case, because we span across the board, we are initially thinking of, while we are constantly developing these platforms, while prioritization, does this feature serve 80% of our user? So we try to prioritize where we can solve for most of the users as of now. Um, all right. I think, and again, when you're developing products, also keep in mind that relevant documentation and training and onboarding and support has to be also figured in and planned for. All right. So in summary, what are some of the best practices that you would like to keep in mind while developing these products? So let's start with automation. Wherever there's a manual process, there's an opportunity for automation. For us, let's imagine we are provisioning these hardware, these machines. If you can provide an interface and ease out the process, then it becomes faster, less errors, less opportunity for human errors, and so on and so forth. So it speeds up the process. Um, Use standard tools as far as possible. So this helps in maintaining and managing a definite set of tools, but at the same time allow users to customize them based on their needs. Um, Next, let's talk about standard processes. In terms of um, in terms of processes, we have employed at several stages standard processes to allocate, to tag our computes, which helps us in making sure that it's streamlined. Everything is streamlined. There is less when you're investigating an issue, so it's not a it's easier. Um, Standard interface. When you are developing these tools, providing standard interface, standard libraries, APIs, allow for better and easier integration. Um, and this also spans well on documentation and training efforts. All right. So strong partnership. When we are working on optimizing and empowering our data science teams developing these tools, we also have to be strongly partnering with different stakeholders. Um, Along with data science teams, we have data engineering teams. There are different initiatives where you could influence and ensure that such best practices are also followed there, that impacts your user. Um, So this is basically a process which you continuously keep educating your users, and you continuously keep learning from your users as well. So let's say you develop new tools, you can push information in terms of release notes, demos, and at the same time keep the feedback loop open using different forums and check-ins with the users. So that's very critical as well. Um, Now I want to talk about the support model. So now as a platforms team, you may continue to add different tools. Um, what you should also remember is or clarify is what the support model is, and who are the owners, which team owns what kind of products, what's the process, and what's the expected SLA on those tools. So this helps avoid confusion and again provide good experience when something goes in a different direction. Um, Finally, success criteria is with these projects or programs. So there is a pilot program that you are working with your users. Ensure that the success criteria is well defined and clear, so everyone can focus, and it also helps in accountability. So those are some of the best practices that we have been following, and has helped us build a good set of tools and to help with the data science use cases. So that's all from my end. Hope you enjoyed the presentation. Let me know if you have any questions. And thank you.